Hello, everyone. It is Tuesday. It is time for another review session. This time we are going to be doing thermodynamics, so unit 6. This is going to involve heat capacity, heat, Hess's law, phase diagrams, phase things, all of that stuff. So if you want to follow along, we're going to be going through a bunch of things. I'll switch gears to my iPad in just a moment. If you want to follow along, I do have the PDF with all of the practice problems on my link tree. So you can go ahead, click that. It'll bring you to a Google Drive. It has all of the PDF of the problem sets that we've done so far, including the answer keys. This one, the answer key is not up yet because we are going through it tonight. But I hope everyone is having a fabulous Tuesday. I think everything is all set. I'm just going to give myself a moment to finish getting everything set up. What is everyone up to? I'm gonna go here. I have 3 or 4 monitors on me. 3 or 4 monitors looking at me. That's what I meant to say. View profile, and then it shows that I'm live so I can see what you are seeing. Could you do an acid-base titration review session? I will be doing an acid-base review session all about acids and bases later on. In the month, probably, I think it's April 27th is that one. But I can definitely look at my schedule to see if I can do a specific one on titrations, because I know it's a lot. I do have a couple videos up right now going over all of the calculations you need for a strong titration, strong acid with a strong base, as well as a weak acid and strong base titration. So all of those calculations you need, I did a video. They are lengthy videos. I'm going to preface that right now. I think each of them is around 10 minutes, but it goes through all of the calculations that you need for those problems. Boom. How's everyone doing? Okay. I have my answer key, I have my iPad, I have y'all watching, I have myself on my screen. I think we are good to go. So today is going to be thermodynamics, like I was saying. This is Unit 6 of AP Chem. This would be, depending on what you're into in like general chemistry, this is going to be the heat capacity, heat, Hess's law, all of that is going to be here. We have a PDF of some practice problems that has 20 multiple choice and I think 8 short answer free response questions. This is available on my link tree if you want to go ahead and follow along or test those problems out yourself. This recording will be on YouTube once I get YouTube set up. I'm going to take all of the recordings from these sessions, as well as, I have a little like Poindexter right there. I'm going to take all of the recordings, all of the things, and I'm going to start posting all of my content on YouTube as well. So you can maybe find a video easier, or if you only need a certain part of a video, you can do that. All of the videos on YouTube will be vertical though, so I apologize for that. Okay, what I'm going to do is I'm going to switch gears. I'm going to move from this tripod to my fabulous setup here. So let's go ahead. You're going to see probably my ceiling for just a moment. Okay, that's my ceiling. I double tapped earlier and it went. So I liked the live. So I need to go to flip camera. And we do this. And that's pretty good. Amazing. Okay. So, like I said, these live sessions are going to be about 5 minutes of me just talking about thermodynamics or talking about the topic, and then we'll go into the practice problems. This one's only just one little slide that we're going to go over. And this intro to thermodynamics is not going to be all extensive. I think with these problems and with this unit, the best thing to do is jump right into practice problems. So that's what we'll do as soon as we just cover some general variables as well as the equations that we'll see this review session and in this unit. So, my setup's a little weird, but thermodynamics. What is thermodynamics? Well, thermo, if we think of heat, like a temperature, a thermometer, whatever it may be, it's the study of how heat plays a role in chemical reactions. And we use the variable Q to signify heat. Q equals MCAT. Yes, don't worry, we're gonna get there. So Q is heat. So anytime we see a lowercase q, that means we are going to be talking about heat. Now, heat typically has a unit of kilojoules. Now, you might see it in joules, but that's just the standard unit that we use is kilojoules. Another thing that we start to see is heat capacity. Now, specific heat capacity, those are all the same, but what is that exactly? Well, each element, each material that we know, water, aluminum, lead, gold, all of those have what's known as a specific heat capacity. And all that is the amount of energy, the amount of heat something can absorb for every gram of it and it's only going to change by 1 degree Celsius. So the amount of energy something can absorb in 1 gram, the amount of energy 1 gram of something can absorb to change 1 degree Celsius. And so we are going to be using this a lot, but what does that mean? What does specific heat capacity mean? If we were to take a look at something that has like a lower heat capacity, compared to something that has a higher. Well, if it has a lower heat capacity, it means it's only going to absorb a little amount of energy before it starts to heat up. Versus something with a very high heat capacity, it's going to absorb a lot of heat, a lot of energy before it really starts to change temperature. If you've ever seen someone either hold fire in their hands or walk on hot coals, they always do something right before they do that act. They always are going to soak their bodies, wherever piece of their body, their hand, their legs, whatever, they're going to soak that in water. And that's because water has a very high heat capacity. And so when they walk on the hot coals or when they, light their hand on fire, for instance, all of that heat from the coals or from the fire or something is being absorbed by that water before it actually starts to heat up. And because it is heating up the water, it's not going to burn that person. So it's shaking in and out. Uh-oh. Oh, it is shaking in and out. It's like a heartbeat. Hang on a sec. What is going on? I wonder if it's trying to focus. I'm sorry, give me 1 second. Let me just zoom out just a bit. Turn off autofocus. I don't know how to turn off autofocus on here. I think that fixed it. I think it was just it was too close. If it starts zooming in and out again, let me know, and I'll try something else. But for now, we'll continue. I think y'all can see it with the camera angle too and the brightness. If it's too bright, let me know and I'll turn it down. So we have our specific heat capacity. And then we also have what's known as our delta H, or our enthalpy change. You will also see this referred to as heat of something, heat of fusion, heat of vaporization. And this is a measurement of kilojoules per mole. So it's very similar to heat, but now we're talking about heat per mole of something. So these two are very, very similar. Heat and delta H, those are very, very similar. Now we get into our equations, right? Yes, it is chemistry. We're going to get into our equations. The first one that everyone should know or should come to your memory is Q equals MCAT, or Q equals M times C times delta T. This is a way for us to figure out the amount of heat that a reaction or something is either absorbing or releasing based on its mass and its specific heat capacity and the change in temperature of whatever it is that we're doing. And we use this equation primarily the most in our unit, in Unit 6. So we have Q equals MCAT, MC delta T. We also have the equation delta H of our reaction equals negative Q of solution over N. So we have delta H of a reaction, that is our enthalpy change for our reaction, and that's going to equal the negative heat of our solution divided by moles. Remember, that's kilojoules for heat, and kilojoules per mole is our enthalpy change. Now you might be asking, well, why would this be the negative of that? Whoops. Why is delta H the negative of Q? Well, when we go through these problems, we'll see that what we can actually measure is the heat of a solution, the heat of the water in our solution. So when we are measuring something, we are going to be looking at water changes, water temperature changes, but that's not the actual reaction that is going on. We could be dissolving something, we could be breaking bonds. And so if we wanted to look at the overall enthalpy change of the reaction, we have to say that it's the negative heat, because heat is going to be transferred completely. We can't create nor destroy heat. You may have remembered that as one of the laws of thermodynamics, right? Thermodynamics. That is, I believe, the second law of thermodynamics, that heat cannot be created nor destroyed. And so we have this reaction that we're going to be using, as well as these two reactions. Now, these look scary. Don't worry, they're not scary. All these are saying is, if we are given something about the bond energies, when we're talking about bond energy now, the energy between like an oxygen and a hydrogen, or the energy between a carbon and an oxygen, we're going to add together, that's what this sum means, the sum of all of our bonds that are broken, and we'll subtract from it the sum, add it all together, of the bonds that are formed. So we have the enthalpies of all of our bonds broken added together minus the enthalpies of all of our bonds formed. And so this will tell us exactly about something that is endothermic and exothermic. So delta H being positive, let's say whoa, what happened? My whole setup just decided not to work anymore. It almost hit me in the face. Give me 2 seconds. That was fun. That was real fun. Oh, goodness. Technical difficulties. I wonder if it's... Well, we'll just keep going. And if something happens, I'll fix it. So if our bonds breaking are larger than our bonds forming of our energies, then we will be endothermic. We have heat that is entering. And then the same thing can be said, well, if our bonds breaking are less than our bonds formed, we'll have a negative delta H, and that gives us our exothermic. We can also just say, if we aren't given about the bonds themselves, like the individual bond energies, we can look at the overall enthalpies of our products or of our, not element, compounds. There we go. So if we had like water plus carbon dioxide as our products, we could just look up the overall enthalpy of our water and of our carbon dioxide and add those two together. It'll all make sense when we go through it. And then the last little piece here is just our delta H total. Let's say we're given 5 different reactions and we wanted to add all of those reactions up to get a 6th reaction. Well, this is called Hess's law. And Hess's law states that if we wanted to figure out the new delta H of that total reaction, we just add up each of the individual enthalpies. So the sum of each of those enthalpies, each of those reactions that we go through, equals the total new enthalpy. And that's Hess's law. There's a little bit more to Hess's law, but we'll go through that in a moment. Now, this is the bare basics of this unit. Very, very brief overview of a couple variables that we use and a couple equations that we use. But this is going to be where we go into our practice problems, and you will start to see some of these topics, some of these units and everything become I don't know what I'm saying anymore. In any case, I do have, if you want the PDF, which we're about to go through, is 20 multiple choice questions and 8 free response short answer questions. I do have it on my link tree. So if you go to the first link, it'll bring you up to Google Drive. You'll have access to all of the units that we're doing, all the practice problems from all of these live sessions, as well as the answer keys, as the answer keys will be posted after that units thing. So we've done kinetics and equilibrium so far, and this is thermodynamics chapter or unit 6. So let's go ahead. We're going to, what happened to my, there we go, there it is. So we're going to go ahead and I am going to turn the brightness down. I'm looking at my screen just to see if you can see this. The kinetics one actually was banned. Someone reported me for misinformation, and I ended up getting banned about 20 minutes into it. So I'm going to host either a makeup one for that, or I'll just record myself going through the problems and I'll post that. But in any case, we'll go through this. If you can see it, let me know. If you can't see it, I will just sort of move it around. But let's go through these multiple choice questions. So for the first one, for a classroom demonstration, a chemistry teacher puts samples of 2 different pure solid powders in a beaker. The teacher places the beaker on a small wooden board with a wet surface, then stirs the contents in the beaker. After a short time, the students observe that the bottom of the beaker is frozen to the wood surface. What is going on with my thing? I am so sorry, y'all. Something is going on with this. Oh my goodness. Give me... I know the setup. It's going crazy. It worked perfectly fine the other day. Let me try something. Okay, we're gonna try this. There we go. Okay, we're gonna try this. See if this works. I'm gonna lower it again so you can maybe see it a little bit clearer. And hopefully it doesn't do the zoom in, zoom out thing like it was. Okay. So we have this one beaker. Let me just kind of re-summarize this question. Hopefully my setup doesn't fall off again. If it does, I will end the live just so I can redo this, and then I'll get set up again, and then I'll go live again. So we have a beaker, and we're going to be adding two things to that beaker, two solids. Now, the solids are going to react in some fashion, and the only thing we're really told is that it's on this wooden board, but the board is now becoming ice. It's freezing around the board. So I'll just put some blue around here to signify that the ice is kind of forming. It's freezing to that. So which of the following is the best claim and justification based on the student's observation? So we have here this heat scenario where we're going from the heat is flowing. So let me restart. When we start these problems, the first thing we want to do is figure out which way the heat is flowing, which way our energy is flowing. Now here, if we're freezing on the outside, that would mean that we're taking energy in to our system. So we're going from the surroundings into our beaker. Heat is flowing from our surroundings to our beaker. So when we have a solution that is taking energy from its surroundings, that is going to be an endothermic chemical change. It needs heat. It's absorbing that heat. If we think of endo and exo, and I didn't really go over this today, but endo and exo, that tells us whether or not we are releasing or absorbing heat. Endo, we can think of as enter, the EN right there. So heat would be entering. This is where we are absorbing our heat. Where exo, we can think of like exit. So we have exiting or releasing heat. And I'll put release here, if I can even spell. So because the outside of the beaker is freezing, it is decreasing in temperature, it's losing heat, so heat is being gained by our beaker. So this reaction is endothermic, so we can cross off A and B. It's taking in heat, and then we are looking at whether or not it is a physical change or a chemical change. And all of these types of reactions where we have a heat change, where we're either releasing heat or absorbing heat, those are going to be, for the most part, chemical changes if we're reacting two things together. So that's going to be a chemical change because the temperature of the beaker and the water on the board decreased as heat was absorbed by the reaction. And that's sort of what we were just talking about. Heat was being absorbed by our reaction to cool down the surroundings. So the correct answer here is choice D. So the surroundings were exothermic. The surroundings, let's think. The surroundings gave heat to the reaction. So the surroundings lost heat where the reaction gained heat. And so because the reaction is gaining heat, it is endothermic. It is absorbing that heat. This one's a tricky one. It's a lot of information in the text for something that is just asking you, is it endo or exothermic? So it's really figuring out what piece of information is key in this question. All right, let's move on to number 2. Which of the following phase changes, so now we're talking strictly about phase changes going from solid to liquid, liquid to gas, gas to solid, involves the transfer of heat from the surroundings to the system. We sort of just did one here, right? We were doing from the surroundings to the system. So let's think about, well, actually, let's take a look at what we have. We have a gas going to a liquid. Well, when a gas goes down to a liquid, it is condensing. That is what that is called. As we go from a gas to a solid, that is deposition or depositing. That's we'll kind of put depositing there. Liquid to solid, that would be freezing. And liquid to gas would be evaporating. So these are our phase changes that we're going through here. We have condensing, depositing, freezing, and evaporating. Now, as we go from a solid to a liquid to a gas, as we go in that direction, we need to put in heat to our system, right? As we go from a solid to a liquid, we need to put in energy to melt whatever it is that we're doing. As we're going from a liquid to a gas, we need to put in energy. But as we go the opposite way, from a gas to a liquid to a solid, we are releasing that heat. We no longer need it. We're kind of cooling everything down. And so here we're asked to figure out whether or not which of the following phase changes involves the transfer of heat from the surroundings to the system. So we want our system to absorb or gain that energy, that heat. And the only one of these that goes from a solid to a liquid to a gas in that direction where we're absorbing heat is choice D, and that is our evaporating. And let's read the reason why. Because NH3 molecules in the liquid phase must absorb energy in order to overcome their intermolecular attractions and become free gas molecules. And that is exactly what we were describing earlier. We needed to put in that energy. How is everyone doing? We have 20 multiple choice that we're going to go through. And then we are going to go through 8 or maybe 8 depending on time. We'll definitely go through some of the free response. A lot of the questions in the beginning are going to be more conceptual, and then we'll get into the math stuff, the calculations. You should make a YouTube channel. You make everything so clear. Thank you. I'm working on making a YouTube channel. The lives from these review sessions will be posted, as well as all of my current content, like educational content. They will be in a vertical format, though. They'll be vertical instead of horizontal. Why isn't this going? There we go. Okay. Let's go on to number 3, which is the top one here. So we have the elements the elements potassium and chlorine react directly to form the compound KCl according to the equation above. So we have this equation above, and we're given a delta H. Refer to the information above and the table below. So the information above is our reaction, and the table below for this next question. Which of the following values of delta H for a process in the table is or are, so we could have more than one option, less than 0 indicates an exothermic reaction. So here we're looking at which one of these 5, 1, 2, 3, 4, 5, yes, which one of these 5 reactions that are sort of stepwise to this overall reaction, which one of these 5 or which ones are exothermic, meaning they release heat. So let's go through and figure out what's actually going on here. So in the first one, we have potassium solid going to potassium gas. That is a phase change. That is a phase change going from solid to gas, and that is sublimation. Sublimation. Now, sublimation goes from solid to a gas. We just said that that is an exothermic reaction. Sorry. Endo, it needs to absorb heat. My apologies. So sublimation, solid, liquid, gas, we are absorbing heat. That is an endothermic reaction. So our enthalpy change will be positive there. Going from potassium to a potassium ion, we are stripping away that electron. And when we remove an electron, that process is positive. We need to put energy in to strip or remove that electron from our potassium. We can't just go in there and say, oh, we're going to take that out and it's going to give us energy as well. No, we have to put in something to remove it. Our chlorine, so Cl2 gas, going to 2Cl. So we're going from a bond. So we have 2Cls bonded together, and we're going to break that bond. In order to break the bond, we're breaking a bond here. In order to break a bond, we need to put in energy. We need to put in heat. And so this is also going to be an endothermic reaction or process. So now we have chlorine gas plus an electron gives us that ion. We're no longer going to... Hi, Liz. Sorry. Liz is a former student of mine. Hi, Liz. We're no longer going to be removing an electron, but we're putting an electron there. We're gaining an electron. And when we gain an electron like this, something that is very electronegative, electron gain, this is going to be an exothermic reaction. So we have an exothermic reaction here because we're gaining an electron. It likes that process. It's going to release that heat. And then here we have our potassium ion plus chlorine ion goes to a potassium chloride salt or solid. Now this, if we go the opposite direction, going from a solid to our gaseous ions, those are actually, that's our lattice energy. Now lattice energy is always going to be positive, but since it's the opposite of lattice energy, that is going to be a negative. So we have opposite of lattice energy. And so we'll have a negative process there. So we have positive, 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 negative, and negative. So the only two, if we go back to our question, that are exothermic are Y and Z, which is choice B. So it looks like a lot right off the bat. But if you break down and just look at, okay, phase change, solid to gas, that's sublimation. We need energy to do that. Beautiful. So that's going to be positive. We're stripping away, we're taking away an electron. In order to do that, we need to put in energy. As long as you sort of break it down step by step like that, these don't become terrible. All right. Took a sip of coffee. And now let's go on to question number 4. A 100-gram sample of metal was heated to 100 degrees Celsius and then quickly transferred to an insulated container holding 100 grams of water at 22 degrees Celsius. The temperature of the water rose to reach a final temperature of 35 degrees Celsius. Which of the following can be concluded? So here, what we're doing is we have water in a beaker, and we are going to take a 100-gram sample of metal. So I'm just going to put like a big block there. And so this metal is at 100 degrees Celsius, and this water is at 22 degrees Celsius. What's going to happen when I add this hot metal to the colder water? Well, heat is going to transfer from the hot metal to the cold water until we get to a solution that is at thermal equilibrium, where our temperature is at 35 degrees Celsius. So this is the concept of what's going on. So which of the following can be concluded? Well, the metal temperature changed more than the water temperature did. Therefore, the metal lost more thermal energy than the water gained. Well, did I read that right? The metal temperature changed more than the water temperature did. Okay, yes. So the metal temperature changed more than the water temperature did. If we look at the temperature change, 100 degrees to 35 degrees, that is a big change compared to 22 and 35. So that is true. But then the second half. Therefore, the metal lost more thermal energy than the water gained. Now, thermal energy, that is our heat. Now, if we remember, second law of thermodynamics, we cannot lose heat. So Q of the metal must equal the Q of the water. It's just going to be the opposite. So the heat that is lost from the metal must equal the heat that is gained by the water. And so because this is saying that the metal lost more thermal energy than gained, that is incorrect. We can just cross that right out. B, the metal temperature changed more than the water temperature did. We found out that that was true from A. But the metal lost the same amount of thermal energy as the water gained. And yes, that is true from above. We just said that the metal lost the same amount of thermal energy as the water gained. So that one is true. I'm going to circle it. And then if we go here, the metal temperature changed more than the water temperature did. Nope, because we already said that that wasn't the case. And the final temperature is less than the average starting temperature of the metal and the water. Therefore, the total energy of the metal and water decrease. That is just not true. We are decreasing one and increasing the other. So that is also false. Yes, these questions are public. So this whole PDF is available to you on my link tree for free. It is, so if you go to my link tree, it's the first link. It'll take you to a Google Drive. And right now I think there's one folder that has all the practice problems in it. This is Unit 6 practice problems. So we can go through those. So you can either follow along or you can try them out on your own. And I will be posting the answer key after this. I take all of these questions. So I will say I don't create these questions. I take them from AP Chem review books. I take them from College Board has a ton of practice problems and old exams, AP exams. So I kind of take a bunch of them from the units and mash them all together. The ones that I think are that often come up. So you have a set of 20 multiple choice and a few short answer, short response as well. All right, let's go on to a graph question. So we have here a couple graphs. Now, I know a lot of you get very, very, very scared when you see these two graphs or a graph of this nature, where we have number of molecules and we have energy. So number of molecules and energy. Now, all this is saying is if we have a bunch of molecules, so let's say we had a big peak like that. If we had a bunch of molecules over on the left-hand side of the graph at lower energies, this means that we're at a colder temperature, right? As we cool down our system, our energy or our number of molecules start to pack up. Think about freezing something. If something's frozen, they're all sort of going down and condensing into one location versus something that is more spread out like this. That means that we're heating it up. Our energy is heating up and our number of molecules we sort of have spread out all over the place. And so all these graphs are telling us is the temperature. But let's go ahead and read the question and see what's actually asking. So the graphs above show the Maxwell-Boltzmann distributions for 1 mole samples of argon. So we have, this is what we call Maxwell-Boltzmann or just Boltzmann distributions. Graph 1 shows the distribution of particle energies at 300 Kelvin. So I'm going to write that right here just so we know, 300 Kelvin. And graph 2 shows the distribution of particle energies at 600 Kelvin. And that matches up to exactly what we were saying, right? Colder temperature, more I guess, a bigger peak, narrower peak, that's the word. And then warmer temperatures, more sort of elongated peak. A student predicts that if the samples are combined in an insulated container and thermal equilibrium is attained, then the most probable particle energy will be between the most probable particle energy will be between the most probable energy shown in graph 1 and the most probable energy shown in graph 2. All this is saying is if we combine them, then the new graph will be somewhere in between. That's what that paragraph is saying. Which of the following is the best justification for the student's claim? Okay. When the samples are combined, the gas particles will collide with one another. We know that that's true. with the net effect being that the speed of the lowest energy particles decreases while the speed of the highest energy particles increase, leaving the average speed of the particles of the original sample unchanged. Well, let's sort of imagine that. If we had sort of a peak right here for the lower energy, and then we had a peak up here for the higher energy, what that's saying is, well, our lower energy ones, those lower speed, lower energy, will slow down. So they're sort of move that way. And then the other ones will move at a higher speed. And so it's sort of moving it away instead of being somewhere in between. So that one is just funky and not right at all. Letter B. When the samples are combined, the gas particles from each sample will collide, still true, with the gas particles from the other sample until every particle in the mixture has the same speed, which is between the average speed of the particles in the hotter sample and the average speed of the particles in the cooler sample. This is the key phrase here, same speed. Now, if we have molecules at different energies, they're going to have different speeds. This is the most probable kinetic energy, right? So if we're colliding them, speed and energy are not the same. So if we have all of our samples at the same speed, we no longer have a new sort of peak here. Instead, we have just a straight line if they're all at the same speed. So unfortunately, B is also incorrect, and it was that keyword same speed there. C, when the samples are combined, the gas particles collide with one another until every particle in the mixture has the same kinetic energy, which is between the average kinetic energy of the molecules in the hotter sample and the average kinetic energy of the particles in the cooler sample. This sounds okay, but it's quantifying it every particle in the mixture. So again, everything has the same speed, every particle in the mixture. That's a quantifier. It is doing, it is getting with, oh my goodness, I'm fumbling on my words. It's a quantifier. It's saying that every single particle, so similar to before where we had that giant peak here, that's what it's going to do. It's no longer going to be an actual curve. It's just a peak. And so that quantifier disallows that to be the answer. So let's see if choice D is correct. If not, then we made a real mistake here. When the samples are combined, the gas particles will collide with one another. We know that's true. With the net effect being that the energy will be transferred from the more energetic particles to the less energetic particles until a new distribution of energies is achieved at a temperature between 300 and 600. And that is going to be our answer because that's saying, well, we have something at a higher thermal energy. We have something more energetic. That's going to transfer that energy to our less energetic until we get a graph that is somewhere in between those two. And so that is our answer. D is our answer. That was a lot of words. Let me know if you have any questions on that one. Oh, I'm going to take a couple sips of my coffee while I catch my breath. This is not an AP practice exam, but these are AP style questions. I take questions from multiple sources and I focus them in on a unit. So this unit is Unit 6, Thermochemistry. And we're doing heat capacity, Hess's law, all of those today. So we're getting into Q equals MC delta T soon. You're cooked for this AP exam. I don't know. Okay, so I'm going to age myself. I don't know if cooked means a good thing or a bad thing now. I'm going to say bad thing like, oh, I'm done for. But if that's the case, no, you're not. You got this. I believe in you. All right, we're going to move on to this one here. Number 6. Where can you find this packet? It's on my link tree. If you click the first link, you'll be taken to a Google Drive that has all of the practice problem packets that we go through. Will you ever go through FRQs? I do every session, yes. So we start off with multiple choice. We start off with 20 multiple choice questions, and then we go into the free response questions. All right. So we have number 6. We are given an equation, xy2 goes to x plus y2. The equation above represents the decomposition of a compound. So remember, decomposition, that's just one thing breaking apart into 2 or more things. The diagram below shows 2 reaction profiles, path 1 and path 2, for the decomposition of xy2. Which of the following best describes the flow of heat when 1 mole of xy2 decomposes? So this is a good question. This is involving a lot of different moving parts. So here, what would be, hello. What would be the cause? This has nothing to do with the question, but what would be the cause to go from path 1 to path 2? What would we need to add, or what was added to go from path 1 to path 2? A catalyst, yes. So a catalyst speeds up a reaction by lowering the activation energy. So if we were to look at this, our path 1, our activation energy, the energy needed for our reaction to even start, so if we kind of climb up this hill, that's called our activation energy. Now, if we look at the activation for path 1 compared to path 2, well, it's much lower, right? And so the only way to really do that, for the most part, is to add a catalyst. It'll speed up that reaction by lowering this barrier, making it easier for the reaction to proceed. Just a little side bit of information there. Let's see, which of the following best describes? So we're looking at this chart here. So let's sort of figure out what this chart is saying. Well, we have 150 kilojoules per mole going from our starting to the top of this peak. So that's our activation energy for path 1. We have 100 kilojoules per mole going from our starting point to our top peak for peak 2, path 2. That's going to be our activation energy for path 2. And then we have 50 kilojoules per mole going from our starting to our ending. That is our delta H, or our enthalpy. Now, if we look here, that value is positive and we're actually increasing, right? We're increasing our energy. We're going from something down here to something up here. And so because our delta H is positive, we are endothermic, right? We're absorbing that heat. We're absorbing that energy. And this means that we are transferring heat from our surroundings, so from wherever we are, to our system. And we're transferring exactly 50 kilojoules per mole, because that is our delta H, is the amount of energy between our reactants and products. And so we are transferring to the surroundings, from the surroundings, my apology. We're going from surroundings to the system. So from surroundings, that's either B or D. So we can cross out A and C. And we said it was 50 kilojoules because that is our delta H. So our choice B is the answer. I saw a couple of you with that in the chat. That's awesome. Good for you. You got it. That was a weird thing for me to say. Yes, path 1 and path 2 in this particular question do not count, or don't matter. It's only the starting and ending, because we just want to look at where that energy started and where it was going. Did it come, if we increased, which we did here, we started and went up, then we were absorbing heat, we're endothermic. But if it was the opposite, if we actually decreased, it would go to the surroundings instead of from the surroundings. That 50 kilojoule difference is not delta G. Delta G, and we'll get to that in a later unit, delta G equals delta H minus T delta S. So that's our Gibbs free energy. It uses delta H, but it's not exactly delta H. So this energy difference here is, why do I have so many dots there? That energy difference is our enthalpy change, not our Gibbs free energy. All right, let's go ahead and move on to number 7. We've seen this reaction before. The elements potassium and chlorine react to form the compound KCl according to the equation above. How much heat is released or absorbed when 0.05 moles of Cl2 is formed from KCl? So now we're getting into a calculation problem. And the way we're going to do this is we're going to set up, let's see if I can write right here. We want to take our 0.05 moles of Cl2, so we're going to start with that value, 0.050 moles of Cl2, and we want to figure out how much heat is released. Well, we're given this delta H value for our reaction, and that's the amount of heat per mole. Something in my kitchen just fell. So that's the amount of heat per mole. So if we were to do dimensional analysis and sort of using these units, not looking at the values yet, but let's use units. We no longer want to be in moles of Cl2. We want to be in kilojoules of heat. Well, now we're going to, I guess you could do it that way. H equals Q over N. That is also true. I'll do it that way in a moment. That way we can see it. So we have this value here, and then we just plug in our values. So for kilojoules, we have -437, and then our stoichiometry here with our Cl2, that is half. So we put sort of half a mole there. So remember, this is per mole, but in our reaction, we only have half a mole. Now, if we were to cancel this out, our units cancel out, and our kilojoules are be what's left, and we end up with a value equaling -43.7 kilojoules. Now remember, this negative sign doesn't appear over here because it's just telling us that heat is being released. Right? If we had a positive value, heat would be absorbing. But that negative just means that heat is released. So 43.7 kilojoules is released, which is choice B. The other way that you can do it is using that one equation that we saw earlier, not Q, but delta H equals Q over N. We plug in our delta H value, we plug in our moles that were given, and then we solve for Q, which is exactly similar to this, just slightly set out a little bit. Yes, yeah, so you're going to do the mole ratio as well, right? So you have the heat, which is this, divided by 0.5. Nice job. All right, now we're going to get into some real good calculations. I know some of you are waiting for the Q equals MCAT and stuff, which is exactly what we're going to get into. So, in an experiment to determine the specific heat of metal, a student transferred a sample of the metal that was heated in boiling water into room temperature water in an insulated cup. The student recorded the temperature of the water after thermal equilibrium was reached. The data are shown in the table, so we're given a bunch of data here. Based on the data, what is the calculated heat absorbed by the water reported with the appropriate number of sig figs? We'll also talk about sig figs here too. So we are looking for Q. Now, anytime that we're looking for Q and we're talking about thermal equilibrium and everything, we are going to want to start thinking of the Q equals MC delta T equation, where we have our heat, the mass of whatever we're talking about, the heat capacity, and then our change in temperature. Q equals MC delta T, Q equals MCAT. You know what I just realized? I've been doing this for so long, and I just realized that Q equals MCAT, people use this equation on the MCATs. I'm sorry, that's just so funny to me. In any case, so here we're going to talk about water. We're seeing what is absorbed by the water. So our heat, that's what we're looking for. Let's look at this table. We have our mass of our water, and then, so actually, let me go back here for a step. Actually, no, wrong problem. I was on the wrong sheet. So our mass of our water is 50.003 grams. And then we have our specific heat capacity of water. That is 4.184 joules per gram degree Celsius. That is a known value, even though it's not in here. I don't think it was set in here. Oh, no, it was set in here. That is a known value. You will always be given that value. So 4.184 joules per gram degree Celsius times the change in temperature. So if we start out at a temperature of 24.95, that's going to be our T initial. And our final temperature is T final. Remember, our final temperature of our metal and our water come to thermal equilibrium. They're at the same temperature. So if we do 32.80 minus 24.95, we end up getting a value that is equal to 7.85. So we can go ahead and plug that value in, and that's in degrees Celsius. Now let's go ahead, and if we were to solve this value out, we would get 1,642.31 joules. But remember, we're asked to figure out significant figures. Or we're asked to figure out heat with the appropriate number of significant figures. When we multiply or divide, we're looking for the least number of significant figures. So we have 5 sig figs here. We have zeros between two non-zero numbers. We have 1, 2, 3, 4, 5. This is a known value. All known values don't necessarily count. But I'm just going to include that here, 4 sig figs, because it doesn't make a difference in this case. So 1, 2, 3, 4, all non-zero numbers. Same thing here, 1, 2, 3. So we have 3 sig figs. So we want to round our answer to the least number of sig figs here. So we want to go 3 sig figs. So 1, 2, 3. That's where we're going to round our answer, meaning our answer here will be 1,640 joules. We're going to round down that 42. We'll round down to 40. So we can go ahead and solve, and that is choice B. Let's take a look real quick at sig figs as a refresher. How many sig figs are in A? Well, we don't see a decimal, so we only count the first 2 digits. Those 2 zeros do not count. That's 2 sig figs. This would be 3 sig figs because that 0 does not count. So there's no decimal. We have 4 sig figs here. All 4 are non-zero numbers. And then we have 5 non-zero numbers as well. So that's 5 sig figs. Amazing. This is a sig fig refresher for y'all. Okay. Number 9. This is where it's going to get a little interesting with that delta H equation. So we have shown above are the equation representing the decomposition of H2O2 and a table of bond enthalpies. So we're talking about bond energies. On the basis of the information, which of the following is the enthalpy decomposition of 2 moles of H2O2? So let's take a look at this equation. We have 2 moles of H2O2. They are breaking down into 2 H2O, 2 water molecules, and 2 oxygen molecules. So what I'm going to do is I'm going to, just off on the side, write out the Lewis structure for the molecule. So we have H2O2, which is H2O and two things. This is notability. I saw that one real quick. And then I'm going to go over here and I'm going to do water. So we have not exactly the Lewis structure, and then we have oxygen, O2. Okay. And we want to figure out the enthalpy of decomposition. So if we were to look at that equation, our delta H is going to equal the sum of our delta H of our bonds that are broken minus the sum of the delta H of the bonds that are formed. And so we have this equation here. It looks scary, but it's not that bad. Let's see how many bonds we have on our reactant side. Well, it looks like we have, well, remember, we have two of these as well. So we have 2 times whatever we have. So we have one OH, but we have 2 of those. So 2 times 2 is 4 OH bonds. And then we have 1 OO bond, but that also is 2 because we have 2 of them, 2 of those molecules. Over on the other side, we have 2 water molecules, so 2 times that. So we have 2 times our water molecules. We have OH and OH, so we have 4 OH molecules, or OH bonds. And then we have 1 O double bond O. So what we're going to do is plug these values in based on however many we have. Our delta H equals, now I'm going to put brackets around here. We have 4 OH, or sorry, other side first, because we're doing, no, this side first. We're doing bonds broken. So bonds broken, our reactants are going to break apart to form our products. So our bonds broken, we have 4 times our OH, which is 463. And then we'll add together, we'll add that to 2 of our OO bonds, single bond, at 146. And that's what this summation symbol means. We're adding everything together. And then we'll subtract from that the sum of our bonds that are formed. So we had 4 OHs. So again, 4 times our 463 plus we have 1 of our 495s. And I'm going to try my best to fit it in here. 495. There we go. Total enthalpy of reactants minus products. Yes, this is the same exact thing. We have total enthalpy of reactants, which is our bonds broken, and then total enthalpy of our products, which is bonds formed. Now, if we were to solve all of this out, I'm going to do it piecewise, but I don't have enough room here. So we have, if we were to solve this first piece out, that's 2,144 minus the second piece would be 2,347. And when you do that math out, you get a negative 203 kilojoules. And that is choice B. Now, if you notice, they did something here where they included both the positive and the negative. So if you did bond energies of your products minus your reactants instead of reactants minus products, then you would get a different answer. So sometimes they like to throw those in. So you want to make sure that you're solving those appropriately. Yay. Okay. I'm going to see. Yeah, we have time. Beautiful. All right. So let's go through onto, whoa, that shrunk very, very little. Let's go through to number 10. Now we're getting into heating curves, right? These are our heating curves. The heating curve for a sample of pure ethanol is provided above. The temperature was recorded as a 50-gram sample of solid ethanol was heated at a constant rate. Which of the following explains why the slope of segment T, so this is segment T right here, is greater than the slope of segment R, which is there. So we're looking at those two values, the slopes of those two values. So let's quickly talk about what a heating curve looks like. So heating curves tell us the phase in which something is at a particular temperature. When we start out at P, that's when we're just going to be a solid. Now, as we see here, we're changing our temperature. So anytime that we're changing our temperature, so like P, R, and Q, P, R, and T, we can use Q equals MC delta T because we're changing our temperature. But in the instance of Q and S, we're not changing temperature. So here, I have to slide a puzzle piece over, which is dumb. There we go. We have to use Q equals our mass times our heat of fusion or vaporization, which is our delta H. And so there are two different things depending on whether or not we're changing temperature or not changing temperature. So as we go, so P is a solid. Q would be our solid melting into our liquid. R would just be liquid. S would be liquid into gas, and T would just be gas. And if you just follow that curve, you'll be able to tell exactly what phase things are in. So here, which of the following explains why the slope of these? Well, all of these curves, heating curves, depend on our specific heat capacity. Right? Because a low specific heat capacity means it's going to be able to absorb a lot of heat. Low heat capacity means it will absorb a lot of heat quickly versus a high heat capacity means it's going to, let me rephrase. Low heat capacity means it's going to absorb heat and change temperature quickly versus high heat capacity means it's going to absorb heat and change temperature slowly because it can absorb more heat. That's what we need. So we don't care about our heat of vaporization of this at all, or heat of fusion, because those have no effect on the slopes of these. They're just energies. So we can cross off C and D. We don't care about those. It's all coming down to specific heat capacity. So let's take a look at A. The specific heat capacity of the gaseous ethanol is less than the specific heat capacity of liquid ethanol. Well, if we look at the gaseous ethanol, that was T. Let me actually erase some of these. So that was T, and we said that T had a greater slope. So T is a greater slope. Now, if it's changing temperature at a greater slope, it's increasing quicker, that means it's going to have a lower heat capacity. Because something with a lower heat capacity means it's going to change temperatures quicker. And so since that has a greater slope, it has a lower heat capacity. So that seems to be true. I'll circle it, but let's just take a look at B. The specific heat capacity of the gaseous ethanol is greater than the specific heat. So it's the opposite. Now, because this is greater than, we know that, or the slope is greater than, we know that it has a lower heat capacity than the liquid. So that is also incorrect. All right, going on into number 11. A 10-gram cube of copper at a temperature T1 is placed in an insulated cup containing 10 grams of water at T2. We know that temperature 1 is greater than temperature 2. Which of the following is true of the system when it has attained thermal equilibrium? So let's go ahead and draw this out. We have this at T2. This is our water. And we have our cube of copper there. And that is at T1. Now, T1 we know is higher. So this is a higher T. And this is a lower T. And we know that higher energy or higher temperature will flow, heat will flow from higher temperature to lower temperature, or higher energy to lower energy. So this is sort of a depiction of what's going on. And then we're given our specific heat capacities here. So let's take a look. The temperature of copper changed more than the temperature of water. Well, we're not given any type of temperature, so we can't necessarily know anything about that. I'll put a little squiggle next to that. The temperature of water changed more than the temperature of copper. Squiggle, that could be true. The temperature of water and copper changed by the same amount, or we cannot determine it. So all of these actually have to do with the amount of temperature that is being exchanged. This is where heat capacities come into play. And this question is just getting us to look at a low heat capacity and a higher heat capacity and what that actually means. Well, we just said a low heat capacity means a greater change in temperature. So a lower heat capacity means that we're going to have a greater temperature change. So since copper has a lower heat capacity than water, we'll see that copper changes temperature more than the water. So the temperature of copper changed more than the temperature of water. That is true. So the correct answer here is choice A. Whew. I forget how much I talk during these. It's a lot of talking. But I love doing it. Yay! Heart. There's people now do hearts like, I don't even know, like this? Is this the... I can't do it, but... All right. Oh, thank you. I love doing it. And then I love doing these lives because then I can take these questions and just post them as well so you can see them. All right, let's go on to number 12. Number 12. Based on the reaction represented by the chemical equation shown above, so we have this chemical equation here, what is the amount of heat released when 4 moles of H2S reacts with 9 moles of O2? So this, I was like, how did you already take a guess? But that's okay. So this is bringing in another unit as well. And this is where we're going to talk a little bit about limiting reactants. We don't know which one to use to figure out the energy that's going to be produced, because one of these is going to be excess. We're going to have excess of our O2 or excess of our H2S. We don't know. But we can figure that out by solving for the amount of heat that is it saying heat released? We can solve to figure out the amount of heat released and then compare those values. And whichever one is lower, then that is going to be the answer. So if we were to start out with our H2S, we are told that we have 4 moles of our H2S. And then we're going to use this equation here. We're going to use this delta H. We want to go into a heat. So we're going into, remember this negative just means released. So I'm going to ignore that negative in our calculation for now. So that means that, actually, no, I'm not going to ignore it. I'm going to keep it. So we have negative 1,120 kilojoules of our heat. Now, if we use our molar stoichiometry, we see that that's for every 2 moles of our H2S. And this gets us to go from moles of H2S, which is what we started with, into some value of heat. And when we do that, we end up getting a value that is negative 2,240 kilojoules. And we're going to do the same exact thing, but with oxygen. So we take our 9 moles of oxygen, 9 moles of O2. We use that same value, negative 1120 kilojoules of our heat, but now our molar stoichiometry is 3. That's for every 3 moles of O2 used. So we have 3 moles of O2 here. And when we do that math out, we end up getting a value of negative 3,360 kilojoules. This is where you compare the values of the heats that you got. But remember, this is where we're going to take a look at that negative sign. That negative just lets us know that we're being released. So if we release 3,360 kilojoules versus 2,240, limiting reactant rules say we go with whichever one is less or produces the least amount of our product. And since heat is our product here, we go with the value that is least, ignoring the negative because that just tells us released or absorbed. And that value is 2,240 because that is smaller than 3,360. So the correct answer here is choice C. If my pen will work, choice C. All right. Whew. Gotta shake it out. Shake it out. All right. The reaction representative of, we'll go on to number 13, goes essentially to completion. So we're taking all of this CH3OH and we're pretty much producing. There we go. Okay. All right. Sorry, my phone said I was at 20%, so I just plugged it in. Okay. So here we say the reaction takes place in a rigid insulated vessel that is initially at 600 Kelvin. Which of the following statements about the bonds in the reactants and products is most accurate? So this is where we're going to compare our bonds of our reactants and products, and we're looking at this value here, our delta H value. And that delta H value comes from the bond enthalpies of so delta H equals, so our delta H is our reactants and our products. So what we're looking at here is delta H of our products minus, so delta H of our products minus delta H of our reactants must be greater than 0 because it is a positive value, right? Because it's positive, we have this relationship here. And that means that our delta H of our products must be, if we add over our delta H of our reactants, we're going to add that over. Our products is greater than our reactants. So the sum of the bond enthalpies of the bonds in the reactant is greater than the sum of the bond in the enthalpies. Well, that's not true because we see products and reactants. The sum of the enthalpies and the bonds of the reactant is less than the sum of the bond enthalpies in the products, and that is our answer. Choice B. I see someone saying reactants minus products. I know it's delta H of products minus delta H of reactants, but I'm going to double check just to make sure that with bond enthalpies, we go reactants minus products or products minus reactants. I'm just going to quickly double check. Where are my notes? In the meantime, if you want to try, I'm looking that up right now. In the meantime, if you want to try number 14 while I look through my notes just to make sure. If I could find it. No, I'm just going to Google it because Google is interesting and fun and has all the answers. Bond enthalpy delta H equation. Bonds broken minus bonds formed. Why can't I find it? Just put it in ChatGPT, bro. I would, but I don't have ChatGPT open. Let me just do delta H equation. I could be getting the unit 6 and unit 9 mixed up. You know what? I'll come back to that. So what I'll do is I'll put a circle around that one. And we'll come back to that. We'll just double check afterwards. Okay. So number 14. According to the information above, what is the standard enthalpy of formation, so delta H of formation, for NH3 at 298 Kelvin? So this one's interesting. This is where we're starting to get into our Hess's law. Now, when we get into Hess's law, any time that we need to reverse a reaction, so let's say we have A plus B goes to C, but we want to reverse that, and we want to go to C to A plus B for Hess's law. Well, that just means our delta H, let's say it's 50, our delta H is now going to become negative 50. We change the sign. So that is one rule for Hess's law. The other rule for Hess's law, in terms of manipulating equations, is if we have to multiply. So let's say we wanted to, instead of A plus B goes to C, we wanted 2A plus 2B goes to 2C. Well, then we would multiply our delta H by 2. So if we wanted 2A plus 2B goes to 2C, well, then our delta H would become 100 because we are going from 50 and we'll multiply it by 2 to get 100. So let's take a look at what's going on here. We are given this equation where we have the dissolution or the decomposition rather of ammonia. So we're breaking ammonia apart and we're given our delta H. But we want to figure out the formation of NH3 instead of the decomposition. So the first thing we're going to do is we're going to flip this because we don't want to start with our ammonia. We want to end up with our ammonia. So we want to flip this. So N2 plus 3H2 is going to give us 2NH3. Now, when we flipped it, our delta H now equals the opposite sign of what we started. So negative 92 kilojoules per mole. But we also just want the formation of one of our NH3s. Here we're producing 2. So what are we going to do? Well, we're going to cut this whole reaction in half. We're going to divide by 2. So we get 1/2 N2 plus 3/2 H2 goes to NH3. And the reason why we can have halves out here, we can have fractions, is because they're diatomic molecules. They only exist as diatomics, meaning they exist in pairs with each other. N2 is just 2 nitrogens and H2 is just 2 hydrogens. And this, because we divided out everything by 2, we're going to divide our new delta H value by 2, giving us a value that is equal to negative 46 kilojoules, which is choice B. Hess's law is fun and interesting. It's like a little brain teaser. All right, we have 1, 2, 3, 4, 5, 6 more multiple choice problems, and then we'll get into our free response. So we have here, a student mixes 50 milliliters of 1.0 molar HCl and 50 milliliters of 1.0 molar sodium hydroxide in a coffee cup calorimeter. And observes the observes the change. It's been a long Tuesday, y'all. Tuesday is the best day, though. The change in temperature until the mixture reaches thermal equilibrium. So all this is saying is we're mixing two things and just waiting for it to become thermally equilibriumized. The initial and final temperatures of the mixture are shown in the diagram above. So we have a temperature here and a temperature here. Based on the results, what is the change in temperature reported with the correct number of significant figures? So let's actually zoom in here so we can see. We have our initial temperature. We have 20 and 30, and it looks like there's 10 ticks, 10 tick marks going there. So each one of those is 0.1. So this would be 20.1. Ooh, I'm just going to do 0.1. 0.1, 0.2, 0.3, so on and so forth. Our value here is between 0.2 and 0.3, giving us 20.2, and then we go one more place, wow. Someone should stop me. This is not points. It's 20 and 30, not 20 and 21. This is 1, 2, 3, 4, 5. So 21, 22, 23, 24, and 25. Not 45, but 25. So sorry, y'all. So here we have, I'm glad y'all are catching it in the chat, keeping me on my toes. So we have 21, 2, and in between 22 and 23. That gives us 22.5. We have to go in between there. I'm sorry I confused y'all. So now let's go over to our final. We have 20. Now that we know these are 21, 22, 23, we keep going. 24, 25, 26, 27, and 28. So this is 28, but we have to do our 0.0 for the least precision. And we're looking for the final, or the change in temperature. So change in temperature, that's just going to be our final, which is 28.0 minus our initial, 22.5, giving us a value that is 5.5 degrees Celsius. Now we want to look at the correct number of significant figures, if this would stop going around. When we add or subtract, we're looking for the least number of decimal places. So least number of decimal places in the top 28.1, that's 1 decimal place. The bottom 22.5, that is 1 decimal place. So in our answer, we have to have the least number, which is 1 decimal place, which will be exactly what we have here, 5.5, which is choice A. Yes, I do share the answer key afterwards. I just don't share it prior to, but it will be in the same folder as the Google Drive that's available on my Linktree with all of these PDFs and everything. Okay. This one is going to use that bonds forming and bonds breaking, or the reactants and products. So while that, go ahead and attempt that one if you want. I will go through it in a sec, but I actually am going to double check this equation because my math might be wrong, and I want to make sure that we go over ones that are going to give you the correct answer. So it looks like, okay, so this one's correct. All right, so where'd my pen go? There it is. So here we have, if standard molar heats of formation of ammonia, NH3, and gaseous water, H2O, so we're given something about this value here and something about this value, are -46 and -242. What is the value of our delta H for the reaction represented above? That R should be over here for represented. So here we're given some enthalpies of formation for each one of these pieces. Well, two of the 4 pieces actually. but we want to figure out the overall delta H. So our delta H at 298, and that's our standard, that is going to equal the sum of the delta H of our products minus the sum of the N delta H of our reactants. So in this case, it is products minus reactants. A lot of the times it will be products minus reactants here. So let's take a look at what this means. Well, this N we know is moles. And so moles, that is just the stoichiometric coefficient, so the coefficient out in front of the balanced chemical equation. Now, what we're going to do is we're going to plug these values in. Well, I'm actually going to write it out the full way first so you can see what it looks like. So we're starting with our products on the product side. Now, we're going to start out with the number of moles of our N2, which is 2, times the delta H of our N2. And we'll add to that, because that's what the sum means, we'll add to that the 6 moles from a stoichiometric of our water times our delta H of our H2O. And those are our products. Then we'll subtract from that the 4 NH3s, so 4 times the delta H of NH3, plus that sum of our reactants, 3 times the delta H of our O2. Perfect. So it's this big, long equation here. It's going to get simplified. Don't you worry. So if we were to start plugging in those values, well, we have 2 times, well, we're not given any sort of information about N2. But that's okay, since N2 is in its elemental form, its delta H equals 0. So that we can just plug 0 in right there. So we have 0 plus 6 times, we were given a value for water. Water is the second one, so negative 242 minus our 4 times NH3, which was the negative 46, plus 3 times O2. Again, our delta H for O2, because O2 is in its elemental form, it is going to have a delta H, a standard enthalpy, equaling 0. And look at that. It just got so much easier, because that's 0 and that's 0. So now when we go and solve, we end up getting a negative 1452 minus, so negative 1452 for that side. Then we have a minus a negative, why am I doing another parenthesis there? 184. And when we do this, a negative times a negative becomes a positive. So really we're adding those two together, or we're adding 184 to that negative 1452, giving us value of 1,268 kilojoules, which is approximately 1,270. If we were to go based on significant figures and some other things, that would be negative there, sorry, negative and negative, giving us choice D. Yeah, so I did double check. Bond enthalpies, it is reactants minus products. Everything else, it'll be products minus reactants. I apologize for the confusion on that one. Any tips for preparing for the chem exam? Lots and lots of practice. If it was an FRQ, do you have to write it all out? You do not have to write out the zeros part. I think that's sort of implied. You might want to make a note off on the side, delta H of O2 and N2 equals 0, just so the graders understand that you know that those are 0. But you don't have to write out the full equation. Lots and lots of practice. You'll want to do, going back to tips, you'll want to do I aimed for my students to do 3 full-length I read that comment. Full-length exams at test conditions or under test conditions. So you get familiarized with the setup, the pacing, and all of that. Galvanic cells is going to be the second half of thermal, which is unit 9, which I don't have the exact dates memorized. If it were an FRQ, would we need to know to make it negative 1270? Is it a sig figs thing? It is a sig figs thing, but I was actually looking at this, and this should have been negative 46.0. That way you got 3 sig figs. If it was just the negative 46, we would have 2 sig figs here. Whoa. So if it was 2 sig figs, it would just become like 1300 or something. This is, if it was an FRQ, I think you would be good. Normally with FRQs, it'll tell you to do significant figures. How often do I do lives? I am doing them, I think, twice a week right now. I have a whole schedule on my pinned video going over all of the different units. And we're breaking it up by units. So this unit is unit 6 thermo. And then the next unit, I think we're going all the way back to unit 1 to start talking about those bonds and stuff, and elements and periodic trends and energies and all of that jazz. All right, we have 4 more multiple choice questions. We're getting through it, y'all. We're going through. So here we have the enthalpy change for the reaction below is negative 860. Based on the standard enthalpies of formation provided in the table, what is the approximate delta H of formation for Fe2O3? So now instead of looking for the overall delta H, we're looking for one of these pieces. Now, these are delta H standard enthalpies of formation. So we're going to use the equation delta H equals delta H products minus delta H reactants, or the sum of those. I don't have a ton of room here, but I'll just sort of write that. Now, we are told our overall delta H. Our overall delta H is that a negative there? It is. Negative 860. And that's going to equal the delta H of our products. Now iron, that is 0, which is told. So our negative 1680 for our Al2O3, that is one of our products, and we only have one of them. Minus, I wrote this in a really poor way, minus delta H of our reactants, which Fe2O3 is what we're looking for. And then our aluminum is 0. So we're going to do our, I'll just put an X here because that's what we're looking for. So if we were to figure this out, we would either add over the 1680 and then divide by -1, or we would add over the X and then add over the 860. It's arithmetic, just adding and subtracting. What I'm going to do is I'm going to add over the X to both sides, so I get X minus 860 equals negative 1680. This is how my brain would do it. And then I'm going to add over that 860 and add over the 860. So then we get X equaling a value of negative 820, which is choice D. Entropy is going to be in the second half of the thermodynamics part, so unit 9. This one is more focused on all of the, like Hess's law, heat capacity, MCAT, all of that stuff. Yeah, perfect. Honor stuff. I'm in chemistry honors. This stuff looks similar. I just finished Stoic. Stoic is so much fun. It's one of my favorite units. It's so fun. Okay, we're on to 18. We got 3 more multiple choice, and then we'll get to some free response. Based on the information for 2 different reactions given above, which of the following gives the quantities needed to calculate the enthalpy change for the reaction represented by the overall equation below? This is all Hess's law, right? We're going to take our 2 reactions that were given, and we're going to manipulate them. We're either going to flip them around, we'll multiply them together, we'll we'll multiply by a value, whatever it may be, and we want to end up with this overall reaction here. And then we want to figure out the delta H. So we want to essentially figure out delta H3. What is that going to be? When I do Hess's law, yes, when I start Hess's law, what I like to do first is look at what's in the final version. So if I were to look here, the overall reaction, I have two NOs in gas form. Well, if I look at my two reactions, I want to figure out where those NOs are coming from, where those nitrogen oxygens are coming from. And they're actually coming from reaction 2. And they're on the right side. And we have the right number of them, actually. They're both on the reactant side, and they both are multiplied by 2, have a stoichiometric coefficient of 2, which is perfect. Next thing, well, we see an O2 here, and we see an O2 here. Well, that's even better, because now we have an O2 as a reactant and an O2 as our reactant. So our NO and our O2 seem to be coming from reaction 2. Then we get into this, we have N2O4. Well, that's coming from reaction 1. I'm going to sort of box that in here in green. That's coming from reaction 1, but it is on the reactant side in reaction 1, and we want it on the product side. So what are we going to do? Well, in order to get it to the product side, we need to flip or reverse this reaction. So if we were to flip or reverse that reaction, we get 2NO2 goes to N2O4. Now our N2O4 is on the product side, which is exactly what we wanted. And then now that we've gone through all three of our overall reaction compounds, we just want to make sure that everything left over, and I'll underline this in red, just so we know we have it, and I'll cross this out since we no longer used it. We want to make sure that everything else cancels out. Well, we see that 2NO2 we didn't have in our overall, and that crosses out with another 2NO2. Perfect. So this, our reaction 1, now that it's flipped, now we reversed it, added together to reaction 2 gives us our overall reaction 3. So what are we going to do? Well, we reversed this delta, or we reversed reaction 1, which means this no longer is net positive, it becomes negative. We took the negative of that delta H. So our delta H3 is going to equal the negative of delta H1, because we flipped or reversed that reaction, and we'll add to it. We didn't do anything to the other one, so we'll add to that delta H2. And so this is what we are working with, and that is actually choice C. So yes, I saw negative 177, I think. That is correct. This one, though, wasn't looking for an actual value. It was looking for more of the conceptual, the concepts behind it. That's the word. There we go. All right, we're going to go through two more. We only have two more multiple choice, and then we'll go into a couple of free response. 19. The enthalpy change for the reaction represented above is delta H1. Delta HT. My apologies. That's a T. This reaction can be broken down into a series of steps as shown in the diagram. So it is Hess's law again. We have overall, so A going to X. That is our delta HT. That is our overall reaction. But we also have these reactions. A can go to B, B can go to C, and then C can go to X. And those are our sort of three sub-reactions that we can add up, and it will overall be A goes to X. So we want to figure out a relationship that must exist between this various enthalpy change. And so we know that Hess's law, the overall reaction, the overall enthalpy of reaction equals the sum of, and they are 1s, 2s, and 3s, good, delta H1, delta H2, and delta H3. So we have our total enthalpy equals the sum of all three of those pieces. Now, looking at our answers, I don't see one that equals this. But what I do see is something similar if we do some math to this. If we were to subtract delta H1, delta H2, and delta H3 from both sides, we would get delta HT minus delta H1 minus delta H2 minus delta H3 equals 0. And that is true. All we did is we subtracted our delta H's, 1, 2, and 3, from both sides, and that gives us choice answer A as our answer. And it looks like number 20 is also Hess's law. Based on the information above, what is the enthalpy change for the sublimation? So sublimation, we're going from a solid to a gas of iodine. So solid here, gas here. Now, if we look at this, again, we're going to pair these up. So we have I2 solid. I2 solid is up here in number 1. I'm actually going to label these 1, 2, and I'll do 1 and 2 so we kind of can talk about this. So I2 solid, that is in reaction 1, and we are going, it is a reactant in both scenarios, but in reaction 1, it is half of I2. So what are we going to do? Well, we're going to multiply this by 2. And if we multiply that by 2, we also have to multiply our delta H by 2. So far, our delta H of 3, I'll make this delta H3, equals what? That's what we're looking for. Delta H3, well, that's going to equal 2 times our delta H1. But then we'll figure out what the other step is that we need. We have our I2 gas right here, and that's on our reactant side, but we want it to be on the product side. We also want one of them and not half of them. So what we're going to do is reverse it or flip it and multiply by 2, which means our delta H2 will multiply by 2 and change the sign. It's going to become negative. So we have here, we're going to add to our delta H3. I'm doing this a weird way. I'm going to actually, because it's actually giving us values, I'm going to solve for that. So our new delta H1 is just 2 times 26, which equals 52. And our new delta H2 is 2 times negative 5, but we also have to change the sign. So that'd be 2 times negative 5 gives us negative 10. Changing the sign gives us a positive 10. Oh my goodness gracious. So if we want to solve for delta H3, we're just going to add up 52 and 10. So that gives us 52 plus 10, which is 62 kilojoules per mole, which is choice E. Whew, that was a doozy. We did a lot of multiple choice. A lot of concepts were done in here. Nice job, everyone. For the sake of time, we are going to do... we are going to do all of the, I don't know. When do you use the total mass of reactants in a calorimeter problem instead of just one? When you're looking at the Q solution. So if you're dissolving a solid into something, that's when you would do the new total mass. So if you took, I don't know, salts and, well, actually, let's do one. Let's do number 1. So number 1, we're given a lot of information here. So we'll sort of pick it all out. A coffee cup calorimeter contains 50 grams of water at 20.73 degrees Celsius. when 2.13 grams of ammonium nitrate are stirred into the water, the temperature falls to 17.41 degrees Celsius. There will almost always be a part in a question that says assume the heat capacity of the resulting solution is the same of water and no energy. That's just letting you know that it's a good calorimeter, that you don't have to account for any negligible changes in heat. Calculate the molar enthalpy of dissolution of ammonium nitrate, a chemical commonly used in the production of cold packs. So if you've ever used an instant cold pack, you may have used one with ammonium nitrate. So what are we looking for? Well, we're looking for the molar enthalpy of dissolution. That is going to be our delta H. And we want to figure out our delta H. Now, this has units of kilojoules per mole. So that's ultimately what we're going to be looking for. But in order to do that, we need to first solve for our heat, which is Q equals MCAT. Good. So we have Q equals MC delta T. Let's go ahead and figure out what values we have. I'm going to write off to this. I'm going to do it off to the side here. I'm going to make like a toolbox. Well, we're given, what are we given? A lot of boxes popping up. We have a mass of our water, so mass of H2O equals 50.00 grams. We have initial of the water, so T initial equals 20.73 degrees Celsius. We have a mass of our, I don't know, I don't want to write that whole thing, but I will. NH4NO3 equals 2.13 grams. What else are we given? We have a final temperature, which is equal to 17.41 degrees Celsius. And that's sort of all the data that we're given. So we are looking for heat. So we want to figure out our heat first. So heat, now this is where the question just came in. Why do we sometimes use just the mass of water, and why do sometimes we use the mass of water plus something else? This all comes from whether or not we're talking about Q solution. And this is going to be Q solution. We are dissolving something, a solid, our pellets, are stirred into the water, and with the resulting solution, we're sort of combining our ammonium nitrate and our water. Whenever we put like a hot iron cube or lead cube or something into it, we're not changing the overall solution. We just have heat being transferred from one to the next. Here, though, we're creating a new solution. So our new solution is the mass of both of those combined, the mass of our water and the mass of our ammonium nitrate. So our new total mass would be 50 plus the 0.00, plus the 2.13, which becomes 52.13 grams. Now the heat capacity of the resulting solution is the same of water, and that will always be given to you. That is 4.184 joules per gram degree Celsius. And then our change in temperature, that's our final minus our initial. So if I were to just do this off to the side, T final minus T initial, that equals our 17.41 minus 20.73. I'm writing a little bit tiny so I have enough room here. So our delta T, that's our T final minus T initial, that is a value that I did not calculate beforehand because I did it all in one step. So I'm just going to write this here. 17.41, I'm going to write it real tiny, minus 20.26. I'm losing 20.73. There we go. Beautiful. When do you know to do heat of water or heat of metal? Most of the time, you will always be doing heat of water. That's just sort of what's... Oh, in terms of this, I'm assuming like heat capacity of water or heat of metal. or in terms of this? Let me know and I'll clarify. So when we go through and solve this out, our Q solution is going to equal negative 724 joules. Capacity, as in the capacity, I think. So capacity will always be, you'll be given one and solving for the other, or you'll be given both. You'll just want to make sure, and we'll go over a problem in a little bit, that everything like Q equals MCAT for one stays the same, Q equals MCAT for the other. So you want to make sure your values you don't do like the mass of water, specific heat of your metal, and then the change in temperature of your metal. You want to keep everything the metal on one side, everything water on the other. So this is our heat. This is our value of heat, but we're not looking for heat. We're looking for our molar enthalpy, which is what we wrote up here, a delta H. So what we need to do is use that delta H equation. Delta H equals the negative Q over N, because our heat of our water, of our solution, is, right, we're transferring heat. So our heat that is absorbed by the solution or released is the opposite of what's being done by the reaction or by our system. So we have our Q, so negative times negative 724 joules, but we don't have moles. Now we can go off to the side. We are given a mass of our ammonium nitrate though. So if we go off to the side, I'm running out of room, I should have started over there. But if we go off to the side, we do 2.13 grams of our ammonium nitrate, 1 mole is to 80.04. We're using the molar mass, 80.04 grams, giving us a value of moles equal to 0.0266 moles. So if we go ahead, if we plug that in, 0.0266 moles, that'll give us a value of joules per mole. I'm going to kind of just go up here. I'm sorry, it's kind of all over the place, but so we end up getting a value that is 223 joules per mole. Now that would be an okay value for you to do for a free response. It didn't specify to do kilojoules per mole, but typically when we do delta H, when we're using delta H values, they are given in kilojoules per mole. So you would just do a simple conversion going from joules per mole to kilojoules per mole by dividing by 1,000 or moving the decimal place over 3. And then we would end up with a delta H equal to 27.2 kilojoules per mole. Beautiful. Let's go ahead. I'm going to do this just so we can use that. I think let's go ahead. What's my favorite part of AP Chem? That's a good question. I don't know. I love equilibrium. Equilibrium and I think maybe thermochem. Not this thermochem. I love this thermochem, but my favorite part would probably be like enthalpy, entropy, Gibbs free energy, the Arrhenius equation, all of those. Acids and bases. I do like acids and bases. Titrations are a lot of fun. Why is there a minus sign in front of this equation? Good question. So this is our solution. So Q solution. I should have written that there. We're looking for the molar enthalpy of our reaction. So our solution, if we think about it, our solution, that's of our water and everything. That's what we can measure our temperature change. We're just measuring the temperature change of the water. But that's not the actual reaction that's going on. The reaction that's going on is the dissolution. So we're kind of breaking apart our ammonium nitrate. And so the heat that is either absorbed or released by the solution is actually the opposite sign of our overall reaction. So there is a negative sign here for Q solution. You could do, if you wanted to, you could do, instead of final minus initial, you could do initial minus final, and then you wouldn't need that negative sign there. But it all depends on what your teacher kind of tells you to do. I like to do it final minus initial, so I don't have to think about whether or not a negative sign has to be there or not. It's just always the same. Final minus initial, and then always negative on that Q. But again, it's whatever you're taught. This is just how I was taught and how I teach people, how I teach my students. Let's go on to the next one, because I think this will help clarify some stuff, and I'll explain it in one way and then I'll do it another way. Well, I won't do it another way, but I'll explain why it works another way. So let's see. A brass ball bearing with an initial temperature of 95.55 degrees Celsius is placed in a thermally insulated beaker containing 125 milliliters of water, and we can assume that the density of water is 1 gram per mil. So we can actually assume that this is 125.0 grams of our water. That might come in handy later. And we're at an initial temperature of 20.50 degrees Celsius. When the two substances reach thermal equilibrium, so we combine the two, their final temperature is, we have a final temperature there. What is the mass of the brass ball bearing? BBB. So this is going to be Q equals MCAT. But we're going to do two of them sort of at the same time. Now, I like to do it one way, and this is how I teach my students. If your teacher shows you a different way, that is totally okay. Just know that you can do it more than one way. What I like to do is set up, well, our Q of our water, the heat that is being absorbed by the water, is going to be equal to the heat that is released by the metal, by our brass. So the heat of our water, when it comes to thermal equilibrium, will be absorbing the same amount of heat as our metal, just one is opposite because one's being absorbed, one's being released. And that's all that negative sign means. Now we know that Q equals MCAT, and we can do MCAT for both of these. So we have MC delta T equals negative MC delta T. And this, everything on the left is going to be for water, everything on the right is going to be for our metal. So we can go ahead and start plugging some things in. What are we given? Well, we have our mass of our water. I'm going to write it kind of further over. So mass of water is 125.0 grams. Then we have our specific heat capacity of water. That is 4.184 joules per gram degree Celsius. And our delta T. Well, our delta T, if we do final minus initial, our final temperature is 26.55, and the initial is 20.50 degrees Celsius. Yes, a video of this live will be posted once I get YouTube figured out. I'm going to start posting a lot of things on YouTube. Let's see. So now we go ahead and we do the other side with the metal. So I'm going to put that negative there so I don't forget about it. But then I'm going to put everything in brackets because that negative will apply to everything. We're looking for the mass of our brass ball bearing. So that is our mass that we're looking for. Now, it didn't tell it in the problem, but our specific heats that would have been given, I just didn't put it in here. It's either going to be in a table in your helpful information, or it will be given in the problem. That is 0.380 joules per gram degrees Celsius. And then again, delta T, we have 26.55. I'm going to write them on top of one another. I'm sorry. Minus, oh, I could just move over. I'm going to do that. 26.55 minus whatever we started with, which was 90 something, 95.55. That was up here. Now we can go ahead and start to simplify all of this. We can multiply all of this out if we were to do the subtraction and then multiply everything out on the left-hand side. We get 3,164.15. Now, you don't have to keep track of units for this, but I am going to do the units real quick. We have our grams canceling out, degrees Celsius canceling out, so that gives us joules. And that's going to equal, if we were to do the subtraction here, we multiply it together, that would become negative m times 26.22. That doesn't seem right. Oh, the negative goes, nope, negative. I'm going to redo that. I'm sorry for confusing you. I looked at my notes and I skipped a step. So this side, the negative stays there. M times this whole thing becomes negative 26.22. And the units here are joules per gram. So the negative will cancel out because the negative times the negative is positive. So really this becomes positive 26.22. And then all we have to do is divide by 26.22. So our mass of our brass ball bearing becomes 121 grams. And the joules would cancel out. And the mass of that brass ball bearing is 121 grams. How is everyone doing? I hope you are having a fabulous Tuesday. We are going through a couple more of these practice problems. I'm going to, let's see. This makes sense. Yay. Let's see. If a question asks for the final temp, would you do the same process? Yes. So we'd use the same exact process. The only thing is you would be given a mass. And then instead of your final temperature, you would just put like TF here and TF here, or X or whatever you needed to do. And then you would just use math and arithmetic to go from, to solve for your variables. You will end up getting an X on both sides, but then you can combine like terms later on. Good question. What chemistry is this? This is AP chemistry. An AP chemistry question, but this is done in general chemistry, so Gen Chem 2 typically. Let's see, what app? This is Notability. I use Notability for all of these. Do you have Hess's Law problems? Yes, we went through a couple multiple choice. I can skip around. We can go to a Hess's Law problem. Let's do that. Let's skip to a Hess's Law, which is right here. So let's go through a Hess's Law problem. So number 7 on the free response, determine the enthalpy change for the reaction. So this is our overall reaction up here. CH4 plus 4Cl2 goes to CCl4 plus 4HCl. So using the following information, and we're given 3 separate reactions. So what I'm going to do is I'm going to label these. Let's see, I'm going to label these. Do I have red on? I don't have red. There's red. 1, 2, and 3. And then this will become delta H1, delta H2, and delta H3, just so I don't get confused in this process. So again, with Hess's Law, the easiest way is kind of like, it's kind of like a brain teaser. So we have to figure out how to manipulate these 3 equations to get, when they add up, when we add the 3 of them up, we need to figure out how to do that so we get the overall reaction. And what I like to do is start with our overall reaction and see where those pieces are in the separate reactions. So let's choose blue first. So we have our first reactant here is CH4. Now, CH4, if we look at our 3 equations, only appears in one place. and that's over on the product side of reaction 1. But we don't want it on the product side. We want it on the reactant side in our overall reaction. So in order for that to happen, we need to reverse or flip reaction 1. Now we don't need to multiply or divide because it's already 1, right? We only have one of them here and we only want one of them. So I'm gonna do this in red, we'll say. So if I go ahead and flip this reaction, we have CH4 now is going to C plus 2H2. That was reversed. And now our delta H1, that's going to get the negative sign. It's going to change sign. So we have 74.6 kilojoules per mole. Yes, we're going to change the sign. That's exactly what we're doing. All right. So now let's go ahead and look at our next reactant. Well, our next reactant is Cl2. And it looks like we have a couple Cl2s here. And whenever we get into a situation where we have more than one Cl2 in more than one reaction with Cl2, I like to skip it because we might be multiplying later on. We might have to reverse something. We don't know. And so I like to skip that. So we're going to skip that Cl2 for now. And we're going to go right along to our products of CCl4. So CCl4, that is a product, and we look at our 3 reactions, and the only place it shows up is our in reaction 2, and it is a product, which is perfect, exactly what we want. And we only want one of them. So it looks like reaction number 2 is not going to change. And I'm going to go back to red. So we have carbon plus 2Cl2, and that's going to produce CCl4. Now, because we didn't change anything, our delta H2 is going to stay the same, that negative 95.7 kilojoules per mole. And then we go to our last product, which is HCl. We want 4 of them. We look down and we see the only place for HCl is our reaction 3 in the products, but we only have 2 of them. So what we need to do is multiply the full reaction by 2 to get to our 4 HCl. So let's go ahead and go back to that red. And then because we're multiplying everything by 2, this now becomes 2H2 plus 2Cl2 goes to 4HCl. And because we multiplied our whole reaction by 2, our delta H3 also gets multiplied by 2, and that gives us negative 184.6 kilojoules per mole. So now what we could do is add all of these up, but I love to double check just to make sure everything worked out. Because remember, we didn't fully check that Cl2. And so I'm going to get a green color here. I'm going to do black. No, I'm going to do green. So let's see. Let's start crossing things out. If we were to add up all 3 of these, anything that appears on both sides of the arrow will cancel out. So our carbons will cancel out. What else do we have? Well, we have H2 and H2. We have 2 of them. Boom. I think that's everything that's going to cancel out. So our overall reaction becomes CH4 plus 2Cl2 and 2Cl2 is 4Cl2. Goes to CCl4 plus 4HCl. And what do you know? That right here, our overall equation that we found, is the overall equation up top. So we know that we manipulated and rearranged and did everything correctly. And now we can go ahead and do Hess's law, which states if this was our delta H of our reaction, or delta H4, our delta H of reaction, that's going to equal our delta H1 plus our delta H2 plus the delta H3. It's just the sum of all of these. So what we do, delta H reaction equals we just plug in 74.6 plus a negative 95.7 plus a negative 184.6. And if we were to solve that out, our overall delta H reaction of this reaction is negative 205.7 kilojoules per mole. And that is Hess's law. One of my favorite things. One of them. I have many, but I saw a comment somewhere in the chat a while ago while I was going through that these can get complicated, and that is true. These absolutely can get a lot more complicated than this. But the general process is the same. Always look with what you want to find overall. Find it in your reaction. If there's more than one reaction that has it, skip it, move on to the next thing, and then work your way out. I hate fractions too. You're not alone. I never like working with fractions in chemistry. I always want to try. Tell me why I saw this on my FYP right when I need help on this, because I am here to help. That's exactly why. Somehow it brought me to you. I don't know if that made sense, but let's go through. Let's see. I'm going to do a couple more. How long have I been on the live? It has been, I think, 2 hours and 16 minutes so far. Let's see, I opened TikTok to procrastinate suddenly. TikTok is becoming more of an educational thing. I mean, obviously there's still entertainment, and I try to entertain it a little bit, but don't worry. These lives will be posted. I need to figure out my YouTube channel, and then I will post it. I see this and immediately have to enter. Absolutely. All right, let's go through. Which ones do I want to do? I want to do... Let's do number 8. Let's go on one more here. We're going to do 2 more free response. So I think that'll take us to 2.5 hours exactly. So we're going to do number 8, which is this one. And then we're also going to do, I'm going to say, number 8, and we'll end on a, I won't say easy one, but a less complicated one. We'll do number 8 and then number 4. All right. So, and if you want this PDF, it is on my link tree. I couldn't think of the word. It is on my link tree. If you click on the first link, it'll take you to my Google Drive where I'm putting all of these PDFs, as well as the answer keys. The answer key for this one will be posted after this live. I do have to double check on one of those problems though before I actually post it, because I think I may have made an error in the calculation. But let's go ahead and work on this question here. So we'll do this one and then one more. What's your YouTube channel name? I am creating one. That's what's causing the issue. I'm going to create one, and then once I create one, I'll make a video telling you what it is, and it'll be in my link tree. But I need to create one and make it chemistry based and not my personal YouTube account. Okay. So here we have the combustion of C2H4. Now remember, combustion, we're going to go over types of reactions in another live. But combustion is a hydrocarbon or some form of a hydrocarbon reacting with oxygen and will always produce carbon dioxide and water. That's always a combustion reaction. So we have the combustion of C2H4 is represented by the equation above. So there's 3 parts here, A, B, and C. Use the enthalpies of formation in the table below to calculate the value of delta H for the reaction. So we want to figure out what our overall reaction enthalpy is. So we want to figure out, oh, I have the wrong one up. Let me go to my notes real quick. There we go. So this is one where we're going to do our favorite products minus reactants. So we have here delta H1 is going to equal the sum of the number of moles of our delta H products minus the sum of the delta H reactants. Now this looks scary. If you're just joining, don't worry. We're going to go through it. Whoa, moving everything. So what this is saying is, well, we have delta H1. That's going to equal, if we were to look at our products, we're going to kind of sum all of our products together. So I'm going to put a bracket here. Now we have 2 of our carbon dioxide. So I'm going to put 2 times the delta H of our carbon dioxide. Plus, there's that sum coming into play. We have 2 of our waters. We have 2 times the delta H of H2O. And we'll close that up because those are our 2 products. And then we will subtract from that the sum of our reactants. In the next day or so is the YouTube channel. Next day or so, I have a couple things I need to do beforehand, but it should be definitely by the end of the week. Then I'll have the YouTube channel up. So this is now our reactants. We have 1 of our C2H4, so 1 times delta H of C2H4, plus 3 of our oxygen. So we have 3 times the delta H of our O2. And that's all that means. This N is the moles, or our stoichiometry, and then the delta H is whatever is given. So here, if we were to plug in delta H1 equals, we put that in brackets, 2 times CO2 is negative 394, plus 2 times, what is this, H2O, which is negative 286. Close that bracket, and all of that is going to be subtracted by 1 times the 52, plus 3 times, and then oxygen is 0. Why is it 0? Well, it's in its elemental form. So I ran out of room. They didn't give me a lot of space in this one. Because part B isn't an actual question in terms of calculation or anything, I don't need this space, so I'm going to use the space down here. So delta H1, that's going to equal, if we were to simplify that, we get negative 1,360 minus, there's the minus, 52, because that was just positive, which gives us a delta H1 equaling the value of, I'm looking at my notes, negative 1,412 kilojoules per mole. And I know it's kilojoules per mole because of the units right up here. And that is our answer for part A. And I'm going to put A there. Beautiful. Now we take a look at this. Now we take a look at B. The energy of the reactants is shown on the energy diagram above. So this is an energy diagram. This is going to look either like this, or it'll look like this. If it's like this, it's exothermic. If it's like the one where it's above, that'll be endothermic. So let's take, it is just kilojoules. My apologies, because we canceled out all the moles. My goodness gracious. There we go. Remember, because this is a mole value, and so kilojoule per mole is here. Mole times kilojoule per mole. I am erasing everything instead of just tapping. Mole times kilojoule per mole is just kilojoules. My apologies. Everything's getting messed up in my brain right now. But this is our energy. We want to draw a horizontal line segment, or a horizontal line, to indicate the energy of the products. Well, we just found out that our delta H, our enthalpy, is negative. And what does a negative delta H mean? So negative delta H means that we are exothermic. And exothermic means we are going to be releasing energy. So if we were to have an energy diagram, our energy of our products would end up at the below the energy of our reactants, which is exactly what we're going to draw. We see our energy here. Our products will end up somewhere, let's say down here. And that's going to be our energy of our products. Now, it doesn't say that you have to put your products, but if you wanted to, you could put 2CO2 plus 2H2O. That way they know you have your products right there. Don't forget, though, there is a second part to B. So sometimes people forget that you have multiple parts to a question. Draw a vertical line now to indicate the delta H for the reaction and label it with the correct value. So remember, delta H, that is the distance or the difference between our products and our reactants. It is the difference in height and energy between these two. So if we were to draw a vertical line, let me just draw like a bloop and bloop. If we were to draw a vertical line, it would be connecting those two. And that vertical line, we said, is negative 1,412 kilojoules. That is the value there. So that is the vertical line telling us the delta H. This is the horizontal line telling us the energy of our products. Based on the information above, so now we're on to part C. Based on the information above, identify the delta H values that should be added together to determine the value of delta H reaction for the following reaction. So this one's worded a little weird. When I first read it, I was like, what is it talking about? This one, I'm actually going to move this up just a little bit so we have a little bit more room. I'll shrink that and kind of put it here. So here we are given this reaction, but we also have this top reaction. So what I'm going to do is I'm just going to write that top reaction above the second reaction here, because we have two reactions now. Can anyone guess what this is going to be when we have two reactions and an overall reaction? I'm going to write this C2H4. If I can actually write C2H4 plus 3O2 is going to go to 2CO2 plus 2H2O. Beautiful. All right. And then we have delta H equaling, for this one, we found was negative 1412. So 1412 kilojoules. Hess's law, yes. So that's exactly what we're going to do. We have reaction number 1, reaction number 2. We have 2 delta H's. This is our overall reaction, so I'll put 3 here, and we're looking for delta H3. So we're going to go through another Hess's law problem. Again, with Hess's law, we start with the overall reaction. Overall reaction, we have C2H4 as a reactant, and then the only place we see C2H4 in our 2 reactions above is in reaction 1, and it's the correct orientation, which is exactly what we want. So what I'm going to do is just sort of keep it like that because we're not changing anything. I'll just keep that C2H4 there. Next thing we want is water as a reactant. We currently don't have any water as a reactant. They're both products, but they're both in they're in 2 reactions. So we're going to skip that. We don't care about that right now because it's in 2 of them. It makes things complicated. We're going to instead take a look at the one product that we want. And that one product is C2H5OH, which if we look, is a reactant on reaction 2. We don't want it as a reactant on reaction 2. We want it as a product. So what are we going to do? We are going to flip the second reaction. Now what I'm going to do is rewrite both of them. So we have C2H4 plus 3O2 goes to 2CO2 plus 2H2O. And then because we're flipping, so that was reaction 1, because we're flipping the second reaction, we get 2CO2 plus 3H2O goes to C2H5OH plus 3O2. Our delta H's, delta H1 is that negative 1412. Delta H2 now, because we flipped it, becomes the positive version of that, 1370. Can we just use the data from the table and the given entropy? Not quite, because we're not told any of like this information from the table. We're not told the entropy of our, I think this is ethanol, in the table. So we can't use that directly. But good thought. I like that thought. So if we were to add these two up, we add that up, we first are going to cross out anything that appears on both sides. We have 2 CO2s on both sides. We have 3 O2 on both sides. And we have water. But now instead of the same amount, we have 2 waters on our products, 3 waters on our reactants, meaning we'll be left with just 1 water. And if we look at this, we have C2H4 plus water goes to C2H5OH, which is exactly what we want as our third reaction. And then all we do is we add those two up. So delta 3H3 equals the negative 1412 plus 1370. And that gives us a value that is equal to something, but we don't need to know the value in this case because it's just looking at identifying the delta H values that should be added together. We don't need to come up with the overall value. All we have to do is say the two values are negative 1412 and 1370. And though that is our answer for that one. Whew. We're doing a lot of math today, y'all. A lot of math. What class is this? This is AP Chemistry questions, but this can apply to really any type of chemistry, like high school chemistry, honors chem, AP chem, even general chemistry, 1 and 2 questions. Oh my goodness, Fluffy! I'll text you after, Fluffy, because I don't know where you are now, but I am traveling back to a certain place in a couple weeks. And if you're still there, I'd love to hang out. I don't know if you still live in that area, but in any case, we're going to go through one more problem tonight. So we're going to go through number 4. Yes, I'll text you. All right. So we're going to go through number 4, which is the bottom one here. And we want to calculate the amount of energy required to heat 25 grams of water, when we're given a heat capacity, from 20 degrees Celsius to 80 degrees Celsius. So what do you think are we going to use? It's going to be a much simpler one than the one that we just did. I can tell you that right now. Yes, I see some things coming in. We're going to use MCAT, exactly. So we want to figure out the amount of energy or amount of heat, energy required to heat. So we want to come up with a heat. So Q is going to equal our MC delta T. Nice job, everyone. So our Q, that's what we're looking for. Q equals our mass of our water is 25.0 grams. Heat capacity, that's given, 4.18. I'm going to add in the 4, actually, 4.184. Typically, you'll see it as 4.184, at least from what I've seen. 4.184 And then our delta T, that is going to be 80 degrees minus, I'll put degrees Celsius here for everyone, minus 20 degrees Celsius. Perfect. And then all we do is we solve this out. We do 25 grams times 4.184. This becomes 60 degrees Celsius because it was final minus initial. We were going 280 from 20. So 80 minus 20 is final minus initial. Q is going to equal, at the very end, 6,276. And that is in units of joules. But now let's go through and figure out significant figures. And for that, I'm going to rewrite this as 80.0 degrees Celsius minus 20.0 degrees Celsius. So here we have 3 significant figures. We have 4 significant figures here. Because that 0 counts because there's a decimal. I'll go back to that. So this is 2 and 5 are non-zero, and a decimal indicates that everything after a non-zero will count. So that's 3 sig figs. We have 4 significant figures here. When we do the subtraction, we end up getting 60.0 degrees Celsius. When we do subtraction, we look at the least number of sig figs. Or sorry, the least number of decimal places. My apologies. So we look here, this is 1 decimal place, this is 1 decimal place. So the answer of this one subtraction should have 1 decimal place, which means that we have 3 significant figures here. So 60.0 degrees Celsius, that is our temperature change. 1 decimal place, but 3 sig figs. So our answer should be rounded to 3 significant figures, because when we multiply and divide, we want the least number of sig figs. So we have 1 sig fig, 2 sig figs. That's the value that we need to round to. So our heat here is actually going to be 6,200, and the 6 rounds up, or the 7 rounds up because of the 6, so we have 280 joules, and that is our final answer. Nice job today, everyone. I'm going to flip the camera around if I can, so we can kind of say goodbye to everyone. If I can find a way to flip the camera. There we go. Amazing. So to answer a couple questions, my previous lives that I do and the ones coming forth are going to be posted on YouTube. I need to finish creating a YouTube account and then upload them. They will be up by the end of the week. I do have a link tree which has the PDFs of the problems that we go over, as well as the answer key. If you click on my link tree, it's the first link, and then it'll take you to a Google Drive, and you can just search through the folders. I am going live, I think it's every Tuesday and Saturday, with a couple exceptions. I think next week on Tuesday, because of the eclipse and I'm traveling, I moved it to Wednesday. I have a pinned video that goes over all of the dates. It's just a picture that has all the dates. The Kinetics live that I was banned 20 minutes in for misinformation, I'm going to post a video on YouTube of me going through all the problems that we were going to go over. And I think that's everything. If you have a specific question that you want me to go over, my DMs are always open, but I can't guarantee that I will be able to get to everyone's question. But if it is a common question, I will make a video on it, or I'll just be able to help you out. I hope everyone has a fabulous rest of their day. Good luck with everything going on this week. You are all amazing. You are wonderful. Wow, I am tired. I'm going to go snuggle with my kitty cat wherever she is, because, yeah. You are amazing. What's my catch line? Remember, that's what it is. And remember, keep on being amazing. You got this. I believe in you. All right. Have a great night, everyone. I'll catch you on the flip side. My next one is Saturday. My next live is Saturday. So Saturday at 5 p.m. Eastern. I will be live. In the meantime, I'll be posting things on my page. But have a wonderful night. Keep on being amazing. You got this.